Hello again. So in my past few videos, I've been showing you examples of formalizations of fairly simple statements in Lean, either statements in universal algebra that didn't require many prerequisites, or fairly well-known statements in root analysis. So here, I would like to give an example of a more realistic formalization task coming from one of my projects, the Polynomial Freiman-Ruzsa project. So this is kind of a more in the wild type of formalization task. And here, this task is significantly trickier. And in particular, the AI tools that were quite useful in the previous examples, they are of less utility currently at their current level of development, although I do expect them to catch up and also be useful for these tools as well. But so basically, I want to illustrate what it is like currently to formalize by hand when the task is too difficult for current AI tools to assist with extensively. So the this project, its primary goal has been completed. We formalized the proof of something called the Polynomial Freiman-Ruzsa conjecture of Cattell and Martin in the case of two torsion groups. But then there was a generalization to M torsion groups that is still in the process of being formalized. This is the blueprint of the formalization process. At the bottom, we have the final theorem, which is a certain theorem in combinatorics about sets of small doubling in finite abelian groups of fixed torsion. We will not focus so much on the specific goal here, but as you can see from the blueprint, this theorem has been broken up into about 40 or 50 odd lemmas and definitions, which will be proven separately. So some of these have ticks next to them, which means that they have been fully formalized. But about half of them still do not have that tick mark. And so we have an incomplete proof currently. So what I'd like to do is formalize some of the intermediate lemmas in here and complete a few more of the tick marks. I'll show you the graphical depiction of this project, which may be a little bit more visually appealing. So this is the blueprint, not just of this particular M torsion result, but of the entire project. Every bubble here represents one lemma. All the rectangles also represent definitions. And they're color-coded. The green bubbles are those bubbles that have been already proven in Lean. And the blue bubbles are the ones that have been, the theorem has been stated, the lemma has been stated, but not yet proved. So for example, one of the lemmas I hope to prove today is this lemma 12.18, which proves a certain inequality between two different notions of distance on random variables on a certain abelian group. Now, for this task, we won't need to know precisely what these definitions, these distances are. There are other lemmas elsewhere in this project that have already established many facts about them, and we'll be taking those lemmas as a black box. So this is one of the advantages of a formalization scheme like this, is that it really modularizes the task of formalizing a very complicated theorem into lots of atomic pieces where you don't need to understand the entire project in order to fill one little piece. So we're going to go back to the specific lemma that we're going to prove, which is this lemma here, which is taken, by the way, directly from the paper that this is based on. So over here, I'm showing a paper of myself with Tim Gowers, Ben Green, and Freddie Manners. This 33-page paper is the paper from which this blueprint is derived, and this claim here, lemma 3.1 part 2, is the claim that we're going to try to formalize. Now, this lemma in the paper, it only had a 3-line proof. It's a consequence of an earlier statement, part 1, which I just spent most of this morning formalizing, actually. So part 1 has maybe a 6-line proof, which I was a bit rusty. It took me longer than I expected to formalize this. But now I'm back up to speed. I expect this lemma to be relatively, this part to be relatively short. So the blueprint basically copies the proof, the 3-line proof from the paper. but it's quite high level. This is not really an atomic line by line proof that we can just hope to get, for example, with AI to formalize. But we'll see how we go with this task. So we're going to switch now to the IDE. Okay. So this is the current state of the formalization process. You can see there's thousands of lines here already. And here is the statement that we're going to try to prove that if you have natural number m bigger than 2, and you have some m double of measure spaces, omega I, and some random variables taking values in a group G. G has been defined previously to be an abelian group. Then there's a certain inequality between a sum of certain distances between xj and themselves, and then some constant times another type of distance. This capital D is called multi-distance. So this is the claim. Based on my experience formalizing the previous claim, we're going to need some additional measurability hypotheses. This statement was formalized without, without proving that it was true. So in the course of formalizing the previous statement, I realized that I needed also some extra hypotheses, like such as omega being a probability measure, the x's need a finite range and be measurable, and so forth. So we will add those in as needed. So just for as a guide, I'm going to just add in the sketch of proof that we're going to use. Okay. So the way we're going to prove this is, so this inequality is going to be a consequence of the previous inequality. So this is an inequality controlling a diagonal distance, dxj, xj. And we had a previous lemma which controlled an off-diagonal distance, dxj minus xk. So the first step is to get a relation between them. Okay, so we're going to have a claim that for all j and k from 1 to m, actually from 0 to m minus 1, I want to show that the distance between xj and xj is bounded by 2 times the distance between xj and minus xk. Okay, so that's going to be our first step. And that's using a previous tool, which is listed here as Ruzsa triangle. So let's go look at it over on the blueprint side. Okay, so we're going to use something called lemma 3.18. So we're going to use a certain triangle inequality that this distance is known to satisfy. Let's have a look at its lean code. All right, so this inequality has a lot of hypotheses, but it is a triangle inequality for distance. Let me just copy this description over here just for reference as I go back to my IDE. All right, so yeah, what we're going to do is that we're going to make this as a calc block. Okay, so we're going to bound the distance between x and j and x of j by the distance x of j and minus xk, and then the distance between minus xk, xj. Oh, that's interesting. Okay, seems like GitHub Copilot may have actually done that for us, except that it didn't quite work, but we'll fix that later. And then we need that to equal. What's going to happen is that first of all, we're going to symmetrize. The distance function is also symmetric. And then that's going to equal what we need. Okay, yeah, sure, by ring identity. Okay, so we need to use the triangle inequality. Okay, so GitHub Copilot tried to help us here, but it's so let's have a look at the symbol. We need artist triangle. The first argument actually, first argument we need is actually we need the measurability of the first variable xj. So that's not, okay, so actually, I think if we just delete these, this might work. Let's see. So what for, okay, we have some, okay, each measure, okay. We need measurability that we don't actually have. So we need to actually put that in. Let's see. What after we define x, we would like a measurability axiom that for all I, we need xi to be measurable. Put that in, we can see if that works. Yeah, so what Ford get up before is that some of these arguments of this method did not need to be specified. So if you look at the spelling of the theorem down here, you'll notice that some of the arguments are in parentheses, which means they are explicit, and some are in curly braces, which is Lean's way of saying that you don't need to specify these arguments. They will try to infer those arguments from context, from all the other information. Okay, so the actual, in fact, there are only two arguments, three actually. We need the measurability of x, y, and z. So that's xj minus xk and xj. Okay, so actually this one will not be right. This will be something which we will work out, and then h. Yeah, we need to give this method a measurability certificate for xj minus xk and xj. But there is an additional problem because this theorem requires these random variables x, y, and z to also have finite range, as you can see over here. And we didn't actually specify that as a hypothesis. So that actually we need to add. So we're going to add that as a hypothesis. And if we're lucky, Lean will be able to use that hypothesis and just fill in the okay, so now we're good. Okay, so we're not done. We have several goals, but it did. Oh, okay. It's complaining that we also need these spaces to be probability measures. Okay, so we also need to add that as a hypothesis. Okay, I think it is probability measure. So we need the measure attached to each of these measure spaces to be a probability measure. Y is not. There we go. And this omega should be omega. Okay. Yeah, so now we're in much better shape. We actually just need to show one more goal, which is the measurability of negative xk. Now, we do know that xk is measurable, and I do know that there's a method called measurable. Okay, so there's a tool, there's a lemma precisely for this, which is the, it's called measurable.neg, which says that if a function is measurable, then its negative is also measurable. And now we've reduced things to the measurability of xk, which, as GitHub supplies, that's exactly h minus k. So that's the first step here. Now, the next claim that I set up is we need to show that this is equal to this. I can cancel off the first term. It's not being relevant. So that should, and this should just be the symmetry. If I'm lucky, Lee might be able to guess it from, no, okay, so it probably has a bit of trouble because it needs some measurability hypotheses, which we don't have yet. Okay, so let me go back to the blueprint. Yeah, one reason why the usual tools are not super useful is because, for example, these AI large language models are not trained on the PFR project. They do have a lot of information about MathLib, which is useful, but the lemmas we're going to use here are not in the central Lean Math library. They're in this separate PFR project. in the future, I would expect to have AI models that can train locally on specific databases. Right now, we actually need the symmetry lemma. It's called artist sim. So we're just going to apply that. Hang on, why was Congra? Congra. Oh, okay. Congra was doing something that was absorbing a lot of CPU. I only wanted to cancel one level of addition here. Okay. Right, I just need this to be true. I will apply symmetry. And when I apply symmetry, oh, I'm done. Okay, so I don't need anything else. All right, that's nice. Slightly surprised. I thought I would need to prove measurability again, but maybe this lemma. Okay. It looks like this lemma turns out to be true even without measurability. So one thing that is interesting when you're formalizing lean is that sometimes the hypotheses that you think are needed to prove a lemma are not actually needed. So when proving theorems about random variables, you would expect you would need the random variable to be measurable. But surprisingly, for some very basic identities, such as the symmetry, that's actually not needed, which is convenient because it simplifies certain proofs. Okay, so we have proven this specific claim. So the way we're going to deal with this is that we're going to use the previous bound, which is this, and then insert this inequality here. All right, so I think, all right, but this is a double sum. And this is an m-1 here, and here there's a 2 times m. So I think what I need to do is to first sum this inequality over all j and k which are not equal. So I'm going to have a second claim that if I sum over j and I sum over k, and then actually I have some notation from this, my previous lemma, and I think I'm actually going to use this. So in my previous formalization, I set up actually some notation for summing over j and k off diagonal sums, and then I proved some basic facts about them. I didn't realize that I would use them again, so I put them inside this previous lemma. But actually, I'm going to need these right now, so I'm going to actually move these out. Okay, so but now I need to change the syntax a little bit. Okay, so I'm going to define a sum notion. Yeah, later on I will fix this. I'll change this sum to something a bit more localized. I don't want to use up the word sum in the global namespace, but so let's take these little lemmas that I had previously derived and convert them into external lemmas. So I had some previous lemmas, and I would actually, I'll make this some implicit because so that's the first lemma. convert similar here. I wonder if I can get Copilot to do this for me. Okay, I think that did what I wanted. Oh, hello. Couple things. Oh, HM. Oh, I need, in some cases, I need a hypothesis, actually. Right, yeah, some of these lemmas require them to be at least one memory. Okay, so that requires a certain amount of fixing. Okay, I think it's having trouble inferring. Yeah, okay. Why is it still complaining here? No, no more complaints. Okay, so I move these outside. So now some of these will need hypothesis. Okay, good. It looks like my previous code compiled. Okay, there is an issue down here, but I will deal with that later. Okay, so the whole thing that was that I had this bound here, which is pointwise for J and K, and I had a previous tool, which I called sum less than or equal to, that if you had two functions and one of them was pointwise bounded by the other, then the sum of them was bounded by the sum, where sum means this off-diagonal sum, which is kind of here, fixed indenting here. So let's go ahead and apply that. So I have claim 2. I just want to let's see, sum less than or equal to okay. I do need this j not equal to k in here, but actually I think the easiest way to do that is to just insert it in the previous claim. So claim 1, I'm going to insert in this useless hypothesis, which is harmless, but it allows me to apply this. Claim why is it complaining now? Oh, I think it's the wrong argument. Let's see. Sum less than or equal to first, actually, it takes two functions and then this claim. If I do that, All right, so that's good. That should give me claim 2. I can see that well, it's not a good idea to call this sum because sum actually means something. Let's say it's called off-diagonal sum. Okay. Fix all these. Some things here need to change as well. Yeah. Okay. These guys need to change as well. Cute. All right. Hang on. There is someone complaining back here. This is diagonal 70. Okay. This guy's going to change as well. All right. Actually, I may as well just recycle this namespace here. Okay, so let's see if it compiles properly. All right, so I've got this claim. All right, now the way I want to use this, okay, so I've got it. On the other hand, I have this other, I want to use the previous lemma, which is that this sum is bounded by m times n minus 1 and dk. So let's make that a new claim. I think I need off-diagonal sum of the function that maps j and k to dxj x minus k. This should be less than, I think, m times n minus 1 times this. So it's just here. Okay. So this should come from the previous. Where is it? I want to apply this. Okay, it's not x minus k, it's minus xk. There's a weird complaint here. Okay, now it's okay. No, it's still complaining. H omega is already a function. I don't need to apply the lambda calculus, but just do that. Okay, so I applied my previous lemma and it went through, but I need to verify 4 things. Let's separate them so I can see them. Okay, the first thing I need to verify is that m is bigger than or equal to 1. I'm already assuming m is bigger than or equal to 2, so that's just linear arithmetic. The next thing is that I need to verify measurability, but where is it? But that is just a claim HMES. Then what's the next goal? Pilot has stalled a little bit. After measurability, the probability measure hypothesis. Yeah, so that's probably just hprob. And then finite range. Oh, that's supposed to be hfin. Okay. I have all my hypotheses for this, I think. It doesn't like this one for some reason. All right. Okay, so I have these 2 claims. Right, I can bound this sum by this. Okay. And then this guy I can simplify, because when I take an off-diagonal sum of a function that depends only on j, that's actually just the sum of that function times m minus 1. So that's actually a claim that I needed previously. I think I called it something like off-diag sum left. Yeah, it's this thing here. While I'm here, actually, just to disable this linter, turn that off. And I think there was also some similar problem here. Okay, so I'm just going to apply this this lemma. In doing so, I noticed that I needed m bigger than 1, so I'll just have that as a claim. So I need it here. Just need to wait for the linter to catch up. Okay, good. All right, yeah, so we now know that m minus 1 times this sum is bounded by the sum of twice xj minus xk minus xk. I need to pull the 2 out as well. So I think I have a tool for that as well, if I'm lucky. No, actually, I only have I only have one for division. I need a corresponding claim for multiplication. That's not what I want. Okay, that's not even true. What I want is to have a function and a constant. I want to say that I can pull out a constant. I need a bound like this. Um, I'm just trying to copy my previous proof. I think I want the sum on the left, right, do that. All right, what are you complaining about now? Oh, I got 3 inputs. Fix the problem. Sum, C times the sum. Ah, good. Okay, it works. And then, okay, and then get up by the rest of the proof. Okay, so I now have a tool that allows me to pull constants out of sum. So I'll just apply that now. Where was I down here? Okay, I can just combine it with my previous. Actually, really, I should call it mo sum, not sum mo. I got left multiplication, so the name convention says to use mo sum. I do that. So I've done 2 rewrites now. Let's see where this gets us. Okay, it's complaining, but it's not telling you why it's complaining. Okay. Okay, good. So I bounded this quantity by twice this quantity here. So this and this need to combine to give me this. So this can be done. Okay, if I'm really lucky, I'll be able to. Okay, no, I wasn't quite that lucky. Okay, so this I think I can do by a calc block. Okay, so the sum I want, I'm just going to add and subtract. Okay, while I'm waiting for that, what's supposed to happen is I'm going to add and subtract. So I'm multiply and divide this. And I'm going to use so slow. I need to have a look at what I'm trying to chain together here. Just clean up here while I'm waiting. Oh, okay. There's one annoying issue here is that m is a natural number and m minus 1 is a natural number. It doesn't have an inverse. Oh, that's annoying. Just temporarily. Except I'm making this real. So what am I trying to do here? Okay, m minus 2 times. So also m is being casted to a real number here. I think, yeah. All right. That. And if I use that other thing, that should be bounded. All right, I think I'm in good shape now. Okay, so I chain together various things that I need. I don't need those arrows here. So that should just cancel to what I want. Okay. Fail to synthesize inverse of r minus 1. Oh. Okay. It's trying to subtract 1 from the entire real numbers rather, because that's not what I want at all. Okay, let's do that. Okay, seems to be a bit confused, but okay, it's finally compiled. All right, so I've got these 4 to finish the proof here. These error messages should go away soon, I think. An artifact of some previous compilation. Yeah, so another drawback of a real-world formalization project is that once you're a couple thousand lines in, the compilation is slowed down quite a bit, at least on my small little laptop. Okay, but I think I set things up so that everything should be good. Okay. So this, actually, I want to be an equality even. So this should just be a canceling operation. Yeah. But I need m minus 1 to not be 0. That's going to be sort that out later. Okay, so okay, this identity should just be followed from show simplification once I feed it the fact that this is non-zero. Hopefully that just works. Okay, that does work. Okay. Now I need m-1 to not be zero. In fact, it's enough to be positive. I'm really lucky that should just follow from linear arithmetic. Since I already know that m is bigger than or equal to 1, there is a tiny issue because m here is a natural number, and here m is a real number. But hopefully Lena is smart enough to figure this out. Unfortunately not. Okay. Here's where the fussiness of Lean is slightly annoying. That m was already proven to be bigger than 1 or equal to 1 in the natural numbers, but I need it to be true also in the reals. And then I should be able to show that therefore m minus 1 is positive. Seriously? You really can't prove this in linear arithmetic? Oh, I want strictly greater. Ah, okay. No, I need, yeah, of course I can't do this because it's equal to 1. Yeah, so I need m to be at least 2. And that should come from my previous hypothesis. Okay. If I feed it that m is at least 2, then you should be able to show that m is minus 1 is positive. Good. All right. So that was a bit silly, but okay, I had made a slight mistake here. All right. Okay, I can see that I'm going to need this elsewhere, so I'm just going to pull that out. All right. So for the second claim, there's this factor of m minus 1 inverse that should just get cancelled. Should happen. Cancel those. And then what's left should just be the claim, actually. Gconco might already solve everything, let's see. Oh, apparently I need a positivity, but this I can do. All right, there's a method. I'll just use the AI to do this. Okay. Of course, if you want to show that the sum is non-negative, then it suffices to show that the individual terms are non-negative. No, didn't give me, it gave me one of the things I needed, but all right, let's go. Okay. There's a method which I think has named something like finset sum non-neg. In fact, it is that. All right, yeah, sum of non-negative functions is non-negative, so that's what I need to apply here. Do that. Hopefully that works. Well, there's more goals. I also need m minus 1, but less than 2. Wait. Actually, some bad things are happening here. This is not what I want at all. Yeah. Oh, it's concurrencing too much. It's trying to make m minus 1 bounded by 2. Okay, I should not use gcongruer here. Okay. First thing I'm going to have to associate multiplication. I need to regroup multiplication like that, and you do it twice. Let's see, can I just gconquer just one level of this? No, there's no such ability. I want to cancel. Wait. It actually solved it completely. All right. I guess it detected the claim, which is what's needed to finish the job. Okay, I will take that. So here, m minus 1 inverse yeah, so again, I need to reassociate the right-hand side. Did this wrong. B times C. Okay. Should do. Break into 2 pieces. I do that. I'm sorry, to group it this way. Group it like this. And if I'm lucky, I should just follow from one of the claims I already have. last thing. Lucky, that should just be a canceling. Simp got this far. Okay, and I need to. It didn't completely close because I just need zooming identity, so I should be able to close with ring. All right. So I did actually finish the proof of this, but it was more annoying than expected. Okay, yeah, so that is a real-world formalization task. Lots of friction still, unfortunately, but it is doable. So yeah, we've completed one lemma in 1 hour. There is a small lean error, which I'll fix later. It's not super interesting. Okay, but thank you for watching.